All right. Hey guys, I'm back. Um, yeah, doing some more streaming. Let me get myself oriented here. I forgot to bring up my Twitch. I want to see all your comments and stuff. We're gonna start reading chapter 8 today. Common collections. Right here. All right. Let's do it. All right. So, common collections. Rust standard library includes a number of very useful data structures called collections. Most other data types represent one specific value, but collections can contain multiple values, unlike the built-in array and tuple types. The data these collections point to is stored on the heap, which means that the amount of data does not need to be known at compile time and can grow or shrink as the program runs. Each kind of collection has different capabilities and costs, and choosing an appropriate one for your current situation is a skill you'll develop over time. In this chapter, we'll discuss 3 collections that are used very often in Rust programming. A vector allows you to store a variable number of values next to each other. A string is a collection of characters. We've mentioned the string type previously, but this is in this chapter we'll talk about it in depth. A hash map allows you to associate a value with a particular key. It's a particular implementation of a more general structure called a map. To learn about the other kinds of collections provided in the standard library, see the documentation. We'll discuss how to create and update vector strings, hash maps, as well as what makes each special. Okay. So, storing lists of values with vectors. The first collection type we'll look at is vect, also known as vector. Vectors allow you to store more than one value in a single data structure that puts all the values next to each other in memory. Vectors can only store values of the same type. They are useful when you have a list of items such as a line of text or text in a file or the prices of items in a shopping cart. To create a new empty vector, we call the vecNew function as shown in listing 781. Okay, yep. So you do let, and this vector is named v, and then you declare the type, which is a vector that contains either 2 numbers, and then that equals vect, and then I guess this indicates it's a double colon notation. I forget what double colon notation means. I think it means that it's a library, or it's a cargo. It's a crate. So you call it vec new, maybe. We'll see. Note that we added a type annotation here because we aren't interested, we aren't inserting any values into this vector. Rust doesn't know what kind of elements we intend to store. This is an important point. Vectors are implemented using generics. We'll cover how to use generics with your own types in chapter 10. For now, know that vect type provided in the standard library can hold any type. When a specific vector holds a specific type, the type is specified with angle brackets. In listing 8.1, we have told Rust that the vect and v will hold the elements of either 2 type. In a more realistic code, Rust can often infer the type of value you want to store once you insert values. So you really need to do this type annotation. It's more common to create a vect that has initial values, and Rust provides the vect exclamation point macro for convenience. The macro will create a new vector that holds the values that you give it. Listing 8.2 creates a new vect i32 that holds the value 1, 2, and 3. The integer types is i32 because that's the default integer type, as we discussed in data types. Because we've given initial i32 values, Rust can infer that the type of v is vect i32, and the type annotation isn't necessary. Next, we'll look at how to modify a vector. Updating a vector. To create a vector and then add elements to it, you can use the push method as shown in the listing. Push. As with all variables, if you want to be able to change its value, you need to make it mutable using the mute keyword as discussed in chapter 3. The numbers we place inside are all of type i32, and Rust infers this from the data, so we don't need the vect i32 annotation. Like any other struct, a vector is freed when it goes out of scope, as annotated in 8.4. The vector gets dropped. All of its contents are also dropped, meaning that those integers it holds will be cleaned up. This may seem like a straightforward point, but can get a bit more complicated when you start to introduce references to the elements of the vector. Let's tackle that next. Now that you know how to create, update, destroy vectors, knowing how to read their contents is a good next step. There are two ways to reference a value stored in a vector. In the example, we've annotated the type of the value and that are returned from these functions for extra clarity. So let's look at this. Let v equal, and then that's the macro of a vector, 1, 2, 3, 4, 5. And this kind of looks like an array, which I guess basically it is an array. So here, let third, and you tell it let third is the name of this variable, and its type is a pointer to a i32, which equals and v. So this is a reference to v element number 2 or 3, because you count 0, 1, 2, which would be the third element. The third element is blank, and then since third points to 3, this will be 3. Let's see here. Match v get 2 dot get 2. Okay, so some third so this is a function called sum that takes value third, and then you pass it in here and you print line, and it does the same thing here. None, print line. So if it matches this, if v.get2 matches third, then it prints line, and if it doesn't, it prints there's no third element. But there's a third element. So I guess there are two ways. You can use the get, which is the opposite of push, I assume. Easy call there. Note two details here. First, we use the index value of 2 to get the third element vector. Vectors are indexed by numbers starting at 0. Second, the two ways to get the third elements are by using and bracket, which gives us a reference, or by using get method and the index passed as an argument, which gives us an option and t. So it's still a reference. Rust has two ways to reference an element, so you can choose how the program behaves when you try to use an index value that the vector doesn't have an element for. For example, let's see what a program does if it has a vector that holds 5 elements and tries to access an element at index 100. Oh, look. You could run it in the book. I didn't know that. That's so convenient. Oh, this code panics. Look at that cute little crab. So, wow, how did I not know that? Was it like that? Is that like that in... I guess it is. Wow. I just never clicked the play button. That's funny. So it says here... So it just won't compile if this is intentional, prefix it with an underscore. Wait, what? Oh. Unused variable. Okay, so if it's an unused variable, you can just put an underscore in front of it. That's interesting. And then here it says main thread main panicked at index out of bounds. The lens is 5, but the index is 10. So really that just does what I think most programming languages would do if you try to, okay. So when we run the code, first array method will cause the program to panic because it references a non-existent element. This method is best used when you want your program to crash if there's an attempt to access an element past the end of the vector. When the get method is passed an index that is outside the vector, it returns none without panicking. You would use this method if accessing an element beyond the range of the vector happens occasionally under normal circumstances. Your code will then have logic to handle having either some and element or none. As discussed in chapter 6, for example, the index could be coming from a person entering a number. If they accidentally enter a number that's too large and the program gets a none, you could tell the user how many items are in the current vector and give them another chance to enter a valid value. That would be more user-friendly than crashing the program due to a typo. When the program has a valid reference, the borrow checker enforces the ownership and borrowing rules covered in chapter 4 to ensure that this reference and any other reference to the contents of the vector remain valid. Recall the rule that states you can't have mutable and immutable references in the same scope. The rule applies in listing 8.7, where we hold an immutable reference to the first element in a vector and try to add an element to the end, which won't work if we also try to refer to that element later in the function. So here we have the macro 1, 2, 3, 4, 5, and then first is a pointer to 1, and then v.push. So we try to push 6 in there, and then we try to reference first again, but since this takes ownership of this value, first no longer has ownership because we pushed it, so this won't work anymore. Oh, this won't let me run it. Code does not compile, of course. attempting to add an element to a vector while holding a reference to an item. Yep. Yeah, okay. Oh. Yeah, you can't push it because first owns it. Because it references here. You would have to go out of scope, I guess. Immutable borrow occurs here. Mutable borrow occurs here. Immutable borrow later used here. I guess, you would have to you would just have to reference the first element rather than using this variable. I think this still works, but this doesn't work, right? Might look like it should work. Why should a reference to the first element care about changes at the end of the vector? This error is due to the way vectors work. Adding a new element onto the end of the vector might require allocating new memory and copying the old element to the new space. If there isn't enough room to pull all the elements next to each other, put all the elements next to each other where the vector currently is. In this case, the reference to the first element would be pointing to a deallocated memory. The borrowing rules prevent programs from ending up in that situation. Makes sense. Yeah, iterating over the values in a vector. If we want to access each element in a vector in turn, we can iterate through all the elements rather than use indexes to access one at a time. So it's a for loop. Let's see. Let v equal vec 13257 for I n pointer to v, print I, which would print 103258. It's very Pythonian right here. This is like so can we iterate over multiple references to each element in a mutable vector in order to make all changes to all the elements? The for loop in listing 5.8 will add 50 to each element. And you can do this because when it's done, it's out of scope and it goes back to the top, and I has a different value. Because you're pointing to a reference, or you're pointing to one individual each time rather than the whole array here. I guess. To change the value that the mutable reference refers to, we have to use the dereference operator star to get to the value in I before we can use the plus equals operator. We'll talk more about the dereference operator and following the pointer to the value with the dereference operator. Okay. So I guess you have to dereference I first, and then what? I guess I gotta wait till chapter 15 to understand how that works. Huh? But this does work. Oh, no output. That's interesting. What does this do? Does this have no output? This one works. This one doesn't work. Maybe I should try my my practice code. Save that. Let's give it a try. Cart Oops. Cargo run. Oh, wait. I'm not printing anything. I guess here, oh, that makes sense. So let's just see how it works then. And v print line exclamation point, and then you do quotes, and then comma I. Right. Yep. That works as expected. What happens if I don't dereference it? Will it compile? Oops. Oh, come on. If you guys notice, I'm using a Ubuntu. Oh, yeah. Cannot use plus equals on and mute integer. And it tells me that I have to dereference it. It's funny. Okay. Well, I guess that's what I gotta do. I'll wait till chapter 15. You gotta wait 7 whole chapters before they tell you how that works. Wow. Using an enum to store multiple types. At the beginning of this chapter, we said that vectors can only store values that are the same type. This can be convenient. There are definitely use cases for needing to store lists of items of different types, which I think that's a tuple can do that. I'm pretty sure. Fortunately, the variants of an enum are definitely defined under the same enum type. So when we need to store elements of a different type in a vector, we can define and use an enum. So we can make an enum called spreadsheet cell, and then we have a vector, and then we can do spreadsheet cell int spreadsheet cell text. Interesting. For example, we can say we want to get values from a row in a spreadsheet in which some of the columns in the row contain integers, some floating point numbers, and some strings. We can define an enum whose variants will hold the different data types, different value types, and then all the enum variants will be considered the same type, that of the enum. Then we can create a vector that holds that enum, so ultimately holds different types. That's interesting. Rust needs to know what types will be in the vector at compile time, so it knows exactly how much memory on the heap will be needed to store each element. A secondary advantage is that we can be explicit about what types are allowed in this vector. If Rust allows a vector to hold any type, there would be a chance that one or more of the types would cause errors with the operations performed on the element of the vector. Using an enum plus a match expression means that Rust will ensure at compile time that every possible case is handled, as discussed in chapter 6. When you're writing a program, if you don't know the exhaustive set of types the program will get at runtime to store in a vector, the enum technique won't work. Instead, you can use a trait object, which we'll cover in chapter 17. Now that we've discussed some of the most common ways to use vectors, be sure to review the API documentation for all the many useful methods defined on vect by the standard library. For example, in addition to push, a pop method removes and returns the last element. Let's move on to the next collection type, strings. All right. Hash maps is shorter than strings. Strings looks quite long. I'm going to try to finish chapter 8 before leaving, but I'm rather tired. I don't know why. I just made this resolution all weird. Hold on a sec. All right, fixed it. I wish I could lock the resolution for this. But anyways. Ooh, let's see. Let's turn on the lights here so that I can see a little bit better. Okay, let's see. Okay. Storing UTF-8 encoded strings with text. We talked about strings in chapter 4, but we'll look at them in more depth now. New rustaceans commonly get stuck on strings for a combination of 3 reasons. Rust's propensity for exposing possible errors, strings being more complicated data structures than many programmers give them credit for, and UTF-8. These factors combine in a way that can seem difficult when you're coming from other programming languages. It's useful to discuss strings in the context of collections because strings are implemented as a collection of bytes, plus some methods to provide useful functionality when those bytes are interpreted as text. In this section, we'll talk about the operations on strings that every collection type has, such as creating, updating, and reading. We'll also discuss the ways in which string is different from other collections, namely how indexing into a string is complicated by the differences between how people and computers interpret string data. What is a string? We'll first define what we mean by the term string. Rust has only one string type in the core language, which is the string slice str. That is usually seen in its borrowed form and str, pointer str. In chapter 4, we talked about string slices, which are references to some UTF-8 encoded string data stored elsewhere. String literals, for example, are stored in the program's binary and therefore string slices. The string type, which is provided by Rust standard library rather than coded into the core language, is a global, mutable, owned UTF-8 encoded string type. When rustaceans refer to strings in Rust, they usually mean the string and the string slice and str types, not just one of those types. Although this section is largely about string, both types are used heavily in Rust standard library, and both string and string slices are UTF-8 encoded. Rust standard library also includes a number of other string types such as OSString, OSTR, CString, and CSTR. Library crates can provide even more options for storing string data. See how those names all end in string or str. They refer to owned and borrowed variants, just like the string and str types you've seen previously. These string types can store text in different encodings or be represented in memory in different ways. For example, we won't discuss these other string types in this chapter. See their API documentation for more about how to use them and when each is appropriate. Okay, creating a new string. As many of the same operators available with vect are available with string as well, starting with the new function. Okay, string new. This line creates an empty string called s, which we can then load data into. Often we'll have some initial data that we'll want to start the string with. For that, we can use toString method, which is available on any type that implements the display trait, as string literals do. So this is a string literal, and then you can toString it to make it not a string literal, I guess. This code creates a string containing initial contents. Now we can also use the function string from to create a string from a string literal. The code in is the equivalent code from above that uses toString. Okay. I guess I like this better. But, you know, because strings are used for so many things, we can use many different generic APIs for strings, providing us with lots of options. Some of them can seem redundant, but they all have their place. In this case, string from, toString do the same thing. So which you choose is a matter of style. UTF-8, we can include any properly included data in them. Oh, yeah. All of these are string values. A string can grow in size, and then contents can change, just like the contents of a vec. If you push more data into it, in addition, you can conveniently use the plus operator or the format macro to concatenate string values. We can grow a string by using the push string method to append a string slice as shown in the listing. Yep. After these two lines, S will contain foobar. The string push string method takes a string slice because we don't necessarily want to take ownership of the parameter. For example, the code in listing 8.6 shows that we would be unfortunate if we weren't able to use S2 after appending its contents to S1. Let's see here. Is this mutable? It's a string. There's a string literal or a string slice. And here we push bar to foo. And then here we format this print line to have bar, which works because this is a string slice and not a string. So there's no, when you add this to this, S1 does not take ownership of bar. Yeah. If the push string method took ownership of S2, we wouldn't be able to print its value on the last line. However, the code works as expected. The push method takes a single character as a parameter and adds it to the string. Listing 8.17 shows code that adds the letter L to the string using push method. Results in lol. Okay. Often you'll want to combine two existing strings. One way to do that is with the plus operator, as shown below. The string S3 will contain hello world. As a result of this code, the reason S1 is no longer valid after the addition, and the reason we use reference to S2 has to do with the signature of the method. that gets called when you use the plus operator. So it takes a string and a reference to a string. And returns a string. This isn't the exact signature that's in the standard library. In the standard library, add is defined using generics. Here we're looking at the signature of add with concrete types substituted for the generic ones, which is what happens when you call this method with string values. We'll discuss generics in chapter 10. This signature gives us clues we need to understand the tricky bits of the plus operator. First, S2 has an AND, meaning that we're adding a reference of the second string to the first string because the S parameter in the add function. We can only add a reference or a string slice to a string. We can't add two string values together, but wait, the type of reference S2 is AND string. It's a reference to a string, not a string slice as specified in the second parameter to add. So why does listing 818 compile? The reason we're able to use AND S2 in the call to add is that the compiler can coerce the AND string argument to an AND string slice when we call the add method. Rust uses a deref coercion, which here turns AND S2 into AND S2 array from end to end. So those two dots mean from, to and from, I guess, kind of. We'll discuss deref coercion in more depth in chapter 15 because add does not take ownership of the S parameter. S2 will be a valid string after this operation. Second, we can see in the signature that add takes ownership of self because self does not have an AND. This means that S1 in the listing will be moved into the add call and no longer be valid after that. So although let S3 equals S1 plus reference to S2 looks like it will copy both strings and create a new one, the statement actually takes ownership of S1, appends the copy of the content of S2, and then returns ownership of the result. In other words, it looks like it's making a lot of copies, but it isn't. The implementation is more efficient than copying. If we need to concatenate multiple strings, the behavior of the plus operator gets unwieldy. At this point, S will be tic-tac-toe with all the plus and quotes characters. It's difficult to see what's going on. For more complicated string combining, we can use the format macro. This code also sets S to tic-tac-toe. The format macro works in a way, same way as printline, but instead of printing the output to the string, it returns a string with the contents. The version of the code using format is much easier to read, and the code generated by the format macro uses references so that this call doesn't take ownership of any of its parameters. Indexing into strings. In many other programming languages, accessing individual characters in a string by referencing them by index is valid and common operation. However, if you try to access parts of a string using indexing syntax in Rust, you'll get an error. Help, the trait index integer is not implemented for string. The error and the note tells the story. Rust strings don't support indexing, but why not? To answer your question, we need to discuss how Rust stores string in memory. A string is a wrapper over a vec U8. Let's look at some of the of our properly encoded UTF-8 examples. So here's Ola. In this case, len will be 4, which means that vector storing the string Ola is 4 bytes long. Each of these letters take 1 byte to encode in UTF-8. But what about the following line? Note that this string is in Cyrillic letter Z, not the Arabic 3. That's how long the string is. You might say 12. However, Rust's answer is 24. That's the number of bytes it takes to encode in UTF-8, because each Unicode scalar value in the string takes 2 bytes of storage. Therefore, an index into the string's bytes will not always correlate to a valid Unicode scalar value. To demonstrate, consider the invalid Rust code. What should the value of the answer be? Should it be 3, the first letter? When encoded with UTF-8, the first byte of Z is 208 and the second is 105, so answer should in fact be 208, but 208 is not a valid character on its own. Returning 208 is not likely what the user would want if you ask for the first letter of string. However, the data that Rust has at byte index 0, users generally don't want the byte value returned, even if the string contains only Latin letters. If and hello 0 were valid code that returned the byte value, it'd return 104, not H. To avoid returning an unexpected value and causing bugs that might not be discovered immediately, Rust doesn't compile this code at all and prevents misunderstandings early in the development process. Bytes and scalar values and grapheme clusters. Oh my. Another point about UTF-8 that there are actually 3 relevant ways to look at strings from Rust perspective: the bytes, the scalar value, and the grapheme cluster. The closest thing to what we call letters, if we look at the Hindi word written in Devanagari script, is stored as a vector of U8 values that look like this. That's 18 bytes and is how computers ultimately stored this data. If you look at them as Unicode scalar values, which are Rust character types, those bytes look like this. There are 6 char values here, but the 4th and 6th are not letters. They're diacritics and don't make sense on their own. Finally, if we look at them in grapheme clusters, we'd get what a person would call 4 letters that make up the Hindi word. Rust provides different ways of interpreting the raw string data that computers store so that each program can choose the interpretation it needs, no matter what human language the data is in. A final reason Rust doesn't allow us to index into a string to get a character is that indexing operations are expected to always take constant time of 1, but it isn't possible to guarantee that performance with a string, because Rust would have to walk through the contents of the beginning to the index to determine how many valid characters there were. Slicing strings. Indexing into a string is often a bad idea because it's not clear what the return value of the string indexing operation should be. A byte value, a character, a grapheme cluster, or a string slice. Therefore, Rust asks you to be more specific. If you really need to use indexes to create string slices, to be more specific in your indexing and indicate what you want a string slice. Indicate that you want a string slice rather than indexing using index notation. with a single number, you can use the brackets with the range to create a string slice containing particular bytes. Here, S will be a pointer to a string that contains the first 4 bytes of the string. Earlier we mentioned that each of these characters is 2 bytes, which means that S will be ZA, which would happen if we used, what would happen if we used 0, 1, we'd get Z, right? The answer, Rust would panic at runtime in the same way as if an invalid index were accessed in a vector. Oh, because that's only 1 byte. That's not 2. I get it. You should use ranges to create string slices with caution because doing so can crash your program. Methods for iterating over strings. Fortunately, you can access elements in a string in another way. If you need to perform operations on individual Unicode scalar values, the best way to do so is to use char method. Calling chars on separates out and returns 6 values of type char, and you can iterate over the results of each element. The bytes method returns each raw byte, which might be appropriate for your domain. This code will print 18 bytes that make up the string. Be sure to remember that valid Unicode scalar values may be made up of more than 1 byte. Getting grapheme clusters from a string is complex, so its functionality is not provided in the standard library. Crates are available in crates.io if this is the functionality you need. Strings are not so simple. Yes, you've made your point. To summarize, strings are complicated. Different programming languages make different choices about how to present this complexity to programmers. Rust has chosen to make the correct handling of string data the default behavior for all Rust programs. This means programmers have to put more thought into handling UTF-8 data up front. The trade-off exposes more of the complexity of strings than is apparent in other programming languages, but it prevents you from having to handle errors involving non-ASCII characters later in your development lifecycle. Let's switch to something a bit less complex, hash maps. All right, let's do it. Storing keys with associated values in hash maps. The last of our common collections is the HashMap. The type HashMap KV stores a mapping of keys of type K and values of type V. It does this via a hashing function, which determines how it places these keys and values into memory. Many programming languages support this kind of data structure, but they often use a different name, such as hash, map, object, data table, dictionary, or associative array, just to name a few. Hash maps are useful when if you want to look up data not by using an index as you can with vectors, but by using a key that can be of any type. For example, in a game, you can keep track of each team's score in a hash map in which the key is a team's name and the values are each team's score. Given a team name, you can retrieve its score. We'll go over the basic API of hash maps in this section, but many more goodies are hiding in the functions defined on HashMap KV by the standard library. As always, check the standard library documentation for more information. Creating a new hash map. You can create an empty hash map with new and add elements with insert. In listing 8.2, we're keeping track of scores of 2 teams whose names are blue and yellow. The blue team starts with 10 points and the yellow team starts with 50. Okay. Note that we need to first use the hash map from the collections prompt portion of the standard library. Oh, you have to import it. Okay. Of our 3 common collections, this one is the least often used. So it's not included in the features brought into the scope automatically in the prelude. Hash maps also have less support from the standard library. There's no built-in macros to construct them, for example. Just like vectors, hash maps store their data on the heap. This hash map has keys of type string and values of type I32. Like vectors, hash maps are homogeneous. All of the keys must have the same type, and all of the values must have the same type. Another way of constructing a hash map is by using iterators and the collect method. So this used insert, okay. Collect method on a vector of tuples, which each tuples consists of a key and its value. We'll be going into more detail about iterators and their associated methods in the processing a series of items with iterators section. The collect method gathers data into a number of collection types, including hash map. For example, if we had the team's names and the initial scores in 2 separate vectors, we could use the zip method to create an iterator of tuples where blue is paired with 10 and so forth. Then we could use the collect method to turn the iterator of tuples into a hash map as shown in Sting 821. So let's see. You have a team. It's a vector with blue and yellow. And we have the scores, and it's a vector with 10 and 50. And so here we have mutable scores, which is a hash map with key and value. And then here we take teams into iter.zip and we zip it initial score into iter, and then we collect it. I guess that's not too bad. I don't know why you have to into iter, but I mean, I guess to zip it, I don't know. What does this convert it to? I guess that you need to, I don't know. A type annotation hash map is needed here because it's possible to collect into many different data structures that Rust doesn't know which you want unless you specify it. For the parameters for the key and value types, however, we use underscores, and Rust can infer the type that the hash map contains based on the types of the data in the vector. And so we'll do, I see, they'll infer these, but you could put the string or I32. For types that implement the copy trait, like I32, the values are copied into the hash map. For values like strings, the values will be moved, and the hash map will be the owner of those values. Okay. And you can only copy if it's on the stack. So I guess this doesn't compile. Yeah. Okay, so let's see. You got a field, a string, another field that's a string, and then you got a mutable map. You make a new hash map, map.insert, field name, field value. But you can't, field name and value are invalid at this point. Try using them to see what compiler error you get. I see. Yep, I'm not going to do that. I trust you. They're invalid because map owns them. We aren't able to use the variables because we moved it into the hash map with the call to insert. If we insert references to values into hash map, the values won't be moved into the hash map. The values that the references point to must be valid for at least as long as the hash map is valid. We'll talk more about these issues in the validating references with lifetimes, chapter 10. Chapter 10 seems big. Accessing values in a hash map. We can get a value out of a hash map by providing its key to the get method. Seems intuitive. They were talking about doing that before. It looks like they do a reference to the team name here, which is blue. But this is a different string than this, which is funny. I wonder if you could use a string slice here. Here, score will have the value that's associated with the blue team, and the result will be sum and 10. Reference to 10. The result is wrapped in sum because get returns an option pointer to a value. If there's no value for the key in the hash map, get will return none. The program will need to handle the option, and one of the ways that are covered in chapter 6, you can iter over key value pairs in the hash map in a similar manner as we do with vectors using a for loop. Oh, interesting. Updating the hash map. Although the number of keys in value is growable, each key can only have one value associated with it at a time. When you want to change the data in a hash map, you have to decide how to handle the case when a key already has a value assigned. You can replace the old value with the new value, completely disregarding the old value. You can keep the old value, ignore the new value, only adding the new value if the key doesn't already have a value, or you could combine the old value and the new value. Let's see how to do each of those. Okay, overriding the value. If we insert a key and a value into a hash map and then insert the same key with a different value, the value associated with the key will be replaced. Even though the code in 824 calls insert twice, the hash map only contains one key value pair because we've inserted the value for the blue team's key twice. So it's 25. The code will print 25. The original value is 10, has been overwritten. Only inserting a value if the key has no value. Okay, and so you can do or insert. It's common to check whether a particular key has a value, and if it doesn't, insert a value for it. HashMap has a special API for this call, entry. Oh, entry. And that takes the key you want to check as a parameter. The return value entry is an enum called entry that represents a value that might not exist. Let's say we want to check whether the key for yellow team has a value associated with it. If it doesn't, you want to insert the value 50, and the same for blue team using the entry API. The code looks like this. The or insert method on entry is defined to return a mutable reference to the value for the corresponding entry key if the key exists, and if not, inserts the parameter as the new value for this key and returns a mutable reference to the new value. This technique is much clearer than writing the logic ourselves, and it in addition plays more nicely with the borrow checker. Running the code in listing 825 will print yellow 50, blue 10, because blue's already there with 10. The first call to entry will insert the key for yellow with value 50, and the yellow team doesn't have a value already. The second call to entry will not change the hash map because blue team already has value 10. Updating a value based on old value. Another common use case for a hash map is to look up the key value and then update it based on the old value. For instance, shows the code that counts how many times each word appears in some text. Use HashMap with the words as keys and increment the value to keep track of how many times we've seen the word. If it's the first time we've seen the word, we'll first insert the value 0. This code will print, let's look at it. Hello world, wonderful world. So here, for word and text.split underscore white space, let count equal map.entry word dot or insert 0 count plus equals 1. Okay. So the split white space method iterates over sub-slices separated by white space of the value in text. The or insert method returns a mutable reference and mute v to the value for the specified key. Here we store the mutable reference in the count variable. So in order to assign to the value, we must first dereference count with the asterisk. The mutable reference goes out of scope at the end of the for loop, so all of these changes are safe and allowed by the borrowing rules. Okay. Hashing functions. By default, HashMap uses hashing functions called SIP-hash that can provide resistance to denial of service attacks involving hash tables. This is not the fastest hashing algorithm available, but the trade-off for better security that comes with the drop in performance is worth it. If you profile your code and find that the default hash function is too slow for your purposes, you can switch to another function by specifying a different hasher. A hasher is a type that implements the build hasher trait. We'll talk about traits and how to implement them in Chapter 10. You don't necessarily have to implement your own hasher from scratch. Crates.io has libraries shared by other Rust users that provide hashers, implementing many common hashing algorithms. Summary. Vector strings and hash maps will provide a large amount of functionality necessary in programs when you need to store, access, and modify data. Here are some exercises you should now be equipped to solve. Maybe I'll try some of these later. Maybe beginning of tomorrow. Yeah, since it's 8:30. Given a list of integers, use a vector and return the median. When sorted, the value in the middle position, and mode, the value that occurs most often. A hash map will be helpful here of the list. Okay. Convert strings to Pig Latin. The first constant of each word is moved to the end of the word. And so first becomes if fray, erst fay. Words that start with the vowel like hey added to the end. Instead, apple becomes apple hay. Keep in mind the details about UTF-8 encoding. Okay. Using a hash map and vector, create a text interface to allow a user to add employee names to a department in a company. For example, add Sally to engineering or add Amir to sales, and let the user retrieve a list of all the people in a department or all the people in the company by department sorted alphabetically. All right, those sound like fun. We'll do some of these. Or I'll do them and I'll give you the answers. I don't know. We'll figure it out. I think, is that commenting? Yeah. Okay, we'll save that. Awesome. I'll see you guys.